I'm going to expect, though, since this is review stuff, for you guys to kind of jump in here. I'm not going to I'll obviously answer questions. But so we're skipping section 6.1, which is what we just did on the warm-up. So hopefully you can kind of remember that. That, by the way, that's about as absolutely as hard as it's going to get on those. So section 6.2 is disc method, washer method, and known cross sections. Okay. All right, so let's just, and I've cut out a lot of material here because we can just get right to it. Here are the formulas that you guys should be kind of familiar with. How do we find this? By the way, this is disc method. Disc method. In other words, there's no hole in the center. The disc method, these are, by the way, they're based off pi r squared, right? Because what is a disc? It's a circle. So this is pi, this is r squared. And then to get all of these discs added together, that's where this whole integration thing comes in. And by the way, remember, integration is a limit. How many discs are we actually generating? Infinitely many. And once we take that limit to as n goes to infinity, we will get the exact volume generated. Now, this is with respect to the x-axis, and of course, we can do it with respect to the y-axis as well. Can you just humor me here and maybe just try to jot this one down? This one works out really well. I'd like you to try to do this one without a calculator. If you need a piece of paper, let me know. I've got some. So it says, find the volume of the solid formed by revolving the region bounded by f of x equals the square root of sine x. And by the way, that's nice, because guess what you're going to do to the square root of sine x? You're going to square it. So this is going to be a very easy integral. But you need to use this formula here. Okay, in fact, let me erase that. You guys probably already very familiar with it. But this is the formula that we're going to use to find the volume generated using disks. Pi, integral from a to b, our big R, that's our big radius, squared dx. I'm going to pause the video here. I'm going to go if you want to follow along. Okay. So our formula is for the volume, pi, integral from a to b of our big radius squared with respect to the x-axis, because we're spinning around the x-axis. Big R here is simply our function f of x. A is going to be 0, that's where we're starting. And b is going to be pi, that's where we're ending. So this volume can be found by pi times the integral from 0 to pi of the square root of sine x squared dx. When we square root, that kind of cancels each other out. So we get pi integral 0 to pi of sine x dx. And what is the antiderivative of sine x? Negative cosine x. So this is going to be pi times negative cosine x, which needs to be evaluated from 0 to pi. Put this in parentheses. Now, let's go ahead and show all of our work here just to make sure we're good. Okay, it doesn't want to let me write that bottom equals. There we go. I'll put it up there then. So we got pi times, okay, so I can do negative cosine of pi. Okay, and then I've got to do minus, if you will, the cosine of 0. And what is the cosine of pi? Negative 1. So we get pi times negative 1. And then minus, what's the cosine of 0? That's 1. So what do I put right here?
Shouldn't it be 1 plus 1?
It is 1 plus 1.
The first.
Oh, wait. You guys said this cosine of pi was negative 1, right?
Yeah.
Negative and negative makes that positive. Okay, I was just getting a little scared there because things weren't going to work out. I was going to get 0, and that's not what we should be getting. So our final answer here is 2 pi. You guys said it correctly, and then I just substituted that in. So it's 2 pi. Turns out it's exactly 2 pi. If you would have done that with your calculator, you would have got 6.24. Okay? 228. You guys remember this? Difficult? No, very simple. Okay. Doesn't really matter the curve. If they give you some goofy function that's more complicated, guess what I would use? Use your calculator. Okay, I encourage you to do a little bit of both. Okay, so that was the disk method. We also have something called the washer method. The idea is pretty much simply this. Once you get your big radius volume, then you've got this hole on the inside, so it's kind of like a donut. So what you've got to do, and if this is our center, or axis of symmetry, if you will, is we're going to take that big outer radius, we're going to calculate that volume, then we're going to calculate the volume of the little inner radius, and then clearly we need to subtract this inner one from the outer one. And so this is our key formula here. Again, this is with respect to the x-axis. We can do the exact same thing with the y-axis. Please note, though, that we've got the big R squared minus the little r squared. This is not big R minus r squared, okay? So you're basically, what we're essentially doing is we're doing 2 of the last problem. Okay, I can't remember if I put a picture on this one or not. I did. Okay, let's just go ahead and work this one out together, okay? I'm going to do this one with respect to the x-axis. Oh, by the way, we should probably sketch a little bit of a picture here. I got one on the next page, but anyways. So we got one function that's the square root function like this. And then we got this one here that's the squared function. So this one goes like this, okay? So this is, I'll call this the g of x. So there's your g of x. And then this one here, I'll call it f of x, okay? So here's f of x. So now we've got this little region here in the middle here. I'll just kind of make it green. We're trying to deal with that guy. We're going to rotate it around the x-axis. And we're going to use our formula. And I always like to start with writing the formula. So the volume here is going to be pi times the integral from a to b of big R squared minus little r squared, in this case dx. Do you guys know what a is? Can you just look and tell me what a is? It's 0. A little harder question. Anybody want to take a stab on what you think v is? If you're not sure, just set these two guys equal to each other, right? So we basically got y equals the square root of x, and we got y equals x squared, right? So how do I figure out where they intersect? Right, so when are they equal? When is the square root of x equal to x squared? Well, clearly 0 and 0, right? Can you think of any other numbers you can put in there? 1. Does that make sense? Now, I could have solved this, but I really didn't want to. Again, if you want to, I guess you can't do that like you can on the smart board. I think the next slide, I actually got the picture, which I know you guys don't have the notes, but the next slide, it's basically, that's the shape we're dealing with here. Okay, so I think we said that was 1. Now, here's the next thing that I would recommend that you do. Let me draw my vertical axis here. Let's do it in black. Let's do our axes in black. So there's the y-axis. Here's the x-axis. Now what I'm going to do let's do purple. This right here, that's big R. That's big R, the longer R. Okay? And then let's use a different color. I'll use gold. Guess what this guy is? If the purple one's big R, then the gold one's little r, small r, okay? So that tells us, and I'll go ahead and write that. I'm writing all this down, so hopefully it's clear. Big R is, it's the square root function in this example. Little r is the x squared. And you might think, well, man, Mr. Allen, that seems kind of weird because I would think x squared would be bigger. It is once you get past 1. Now, by the way, I should maybe add this too, just in case you're not sure, because it doesn't really specify here. Why am I not worried about that area out there?
It's not closed off.
It's not bounded. So guess what this area is out here? It's infinity, so that's not even a value. We can't assign a value to that. So that's like if we go back to section 6.1, we talk about the enclosed area. Okay? So we are rotating. In fact, I'm going to go forward again. Oops, one too far. So here's that square root function. Here's the x squared function. We're rotating this around. So that's kind of the graph we're going to get. I don't know how you would describe that, honestly. I don't know what shape you would call that. Okay, anyways, I think we got all we need now, right? Okay, so let's go ahead and work it out. Let's do it in black. So the volume is going to be pi integral from 0 to 1 of big R squared. Now, big R is the square root of x squared minus little r, which is x squared squared dx. There's my integral. And again, we can use our calculator if we want to do this, but this one actually works out really well. That's why I did it in class. Guys, I'm trying not to get hung up on the details with like hard functions. The main thing is you guys got to know how to get the formula set up and know the formula. Okay, so we got pi. So that's just going to be the integral from 0 to 1 of x squared. I'm sorry. That's just going to be x, isn't it? Not x squared. Let's try that again, Mr. Allen. When you square the square root of x, you're just going to get x. Here we go. Minus, parenthesis, and then that's going to be x to the 4th, and then dx. Now I've got to do the integration. Of course, the integral of x is x squared over 2. The integral of x to the 4th is x to the 5th over 5. And then we've got to evaluate that from 0 to 1. Now, of course, when I plug in 0, what am I going to get? So that doesn't really matter. So I just need to plug in 1. So I think that's going to give me pi times, I think that's going to be a half minus a 5th, if I'm not mistaken. So that'd be what, 5/10 minus 2/10 is 3/10. So 3 pi over 10. And again, if you wanted to use your calculator to verify that, you could. I'm going to double check that I got the correct result there, but I think I did. Yeah. Questions on that one? So basically, this is the same thing that we just did. It's just you're kind of like doing it twice. I personally, now you guys have to give me feedback. Do you guys find these very difficult? And I feel like on the AP exam, if they give you problems like this, I feel like most students feel pretty confident about getting some points there. The very least, you should be able to maybe get some stuff set up. If it was the no calculator, you might kind of freak out because sometimes they don't make these so easy, right? And you're integrating, the natural log of some crazy thing or something. Right? Questions? Okay. Enjoy. This is the last review stuff. Okay, last thing. No cross sections. This is the part, I think these are actually harder in my experience in teaching this class. I feel like these are a little bit harder. The formula is actually easier. It's simply the integral from a to b of whatever the area function is with respect to the x-axis, or if it's in terms of the y-axis. Now you have to kind of visualize these. So in this case, here's an example of one where we're integrating with respect to the x-axis. So it almost looks like we maybe have two curves coming to a point here. And then we get this slicing effect. Sort of essentially doing the exact same thing, except now we're not rotating it around an axis. We're actually projecting, if you will, a shape. And that shape could be anything. The shape could be a square. It could be a semicircle. It could be a rectangle. What are some of the other ones? An equilateral triangle. It's kind of funny. Over break, so you guys know, like the video I'm working on today, I worked on right before fall break, and that's for section 7.4, 7.5. Anyways, so I posted the video that I made for this like a month and a half ago or something like that. Over break, someone from somewhere in the world like posted a question on my YouTube channel about this particular problem. Not this particular problem, but this concept. Can you explain that a bit? And it actually, I got really excited because it was the first time, the person's name was like Galactic something or other, but it was like a very well worded question, and I was like, this is so cool. Anyways, sorry. Okay, so, all right. So there's kind of a lot going on here. Can you guys kind of think of the XY plane right now? So ignore this like darker navy blue thing. See the y-axis and the x-axis. So I'm trying to make it look three-dimensional here. You see this light blue curve here. That's the parabola y equals x squared. Does that make sense? Okay. So if we think about this, and I'm going to end up erasing this. Let's see if I can do a highlighter in blue. Ooh, light blue. Let's do that. So this area right here, and I'm going to erase all of that stuff right now. Can you visualize that? So that's on the XY axis, if you will, that's flat on the ground. So that's, if you will, that's kind of like the base of this shape that's going to, this three-dimensional object that's going to protrude from the XY axis, making three dimensions. Does that make sense? Okay, so now I'm going to erase all of that. Now what we're going to do is we're actually going to take, let's get off the highlighter. Now what we're going to do is we're going to take a shape, in this case it's a square. Okay, we're going to take a square and we're going to project it along this curve. So there's going to be like a little bitty square projected right here. There's going to be a bigger square projected right here. There's going to be an even bigger one. Let's see if I can draw this one here. This is going to be interesting. Something like this. So there's a bigger square even right there. Can you kind of visualize those squares projecting out? So that's going to make some kind of interesting three-dimensional thing that maybe some 3D printer could do. And what we're trying to do is we're trying to find the volume that's generated, and it's constricted by these variables. Okay? Again, I'm going to erase everything I have here on the slide. So here's what it says. Find the volume of the solid produced by the known cross-sections where the curve is, and we've already established what that is. It's y equals x squared. That's this curve right here. We're going to go from y equals 0 up to x equals 4. I'm sorry, this curve, and this is the y equals 0 part right here. This is y equals 0, right? And then we're going to go from 0 all the way up to x equals 4. Does that make sense? So our formula, again, is going to be volume equals the integral from a to b of our area function dx. Now, the easy part of all of these, I think finding a and b is pretty easy on these problems. Would you agree? What's a here? It's 0. What's b? It's 4. Guys, we're integrating with respect to the x-axis. Where are we starting? 0. Where are we ending? 4. That's it. The hardest part on these is actually trying to figure out what you are going to put into this. That is, this area function is based on whatever the known cross-section shape is. And like I said in the previous slide, it can be all kinds of different things. In this particular case, I have selected squares. So each shape is a square, and there's infinitely many of them. How do we find, in fact, I'll do this in red, how do we find the area of a square? Well, we take the length of one of its sides and square it, though. That's kind of ridiculous for me to even say that. But here's the thing. This is why this one's a little bit different. What is this length from here to here? What is that length? It's x squared. It's the y value, right? And what is y? It's x squared. So my square is not x by x in this example. It's actually x squared by x squared. Does that make sense? So that means my area function in terms of x, notice here I wrote it kind of in terms of s, if you will, is going to be x squared squared, or x to the 4th. And now we can solve this guy. So the volume is going to be equal to the integral from 0 to 4 of x to the 4th dx. Integral of, or the antiderivative of x to the 4th, I think again is x to the 5th over 5. And we need to evaluate that from 0 to 4. Of course, when we plug in 0, we're going to get 0. When we plug in 4, we have to do 4 to the 5th. 16, 64. I don't know what that is. Is it 256 by chance?
It's 1,024.
I was off. 1,024 divided by 5. So that's going to be, let's see here, 2, then 0.
It's almost 2.
Excuse the interruption. This is a reminder that some things have just changed because of the bell schedule today. We will be
that
having
right?
3 lunches from now until Christmas break. 3 lunches A, B, and C. So if you have a 5th period class, please think about what that 5th period class is right now. If you are in an EL class, you have a lunch.